Hey everyone, we're here today to do the next in the series of challenge discussions on the future of technology and science and society. Today we're going to be focusing a little more on medical research and biological research overall, so taking a little bit of a break from some of the internet policy topics that we've largely focused on so far. Today we're at the Biohub in San Francisco, and I'm here with Professor Stephen Quake and Joe DeRisi, who are co-presidents of the Biohub. And the Biohub is it's a research lab that is basically a collaboration between three of the top universities in the area. So you got UCSF, Stanford, and UC Berkeley. And we actually, through our philanthropy at the Chan Zuckerberg Initiative, helped set this up initially, and we're really proud of all the progress that they're making here so far. But we've gotten a chance through this to get to know Steve and Joe, who are two of the most talented and accomplished scientists in the field. And I'm really excited to just have the opportunity today to talk about some of the things that you're excited about, but also some of the challenges in science and how some of the broader policy issues and trends going on in the world and challenges that society faces are impacting science as well. So today we have Steve Quake is here. Steve is probably best known for his work pioneering a technique that I guess is best called liquid biopsy. So the basic idea is that you can take some blood in a blood test, and now you can sequence the blood. So you basically have a sense of what the DNA of the person is, the sequence of the person who you've taken the blood from. But at the same time, you can also sequence the DNA of fragments of whether it's viruses in the blood or cancer cells or other things that might be going on in a person's body to get a sense of what else is going on in there. And it's a really important technique that is going to help in diagnostics around a lot of different types of diseases. I'm sure we'll talk about this a bit today, but probably the biggest advance that this has created so far is replacing amniocentesis for a lot of pregnant women, right? It used to be that you had to get this big needle put in order to do a Down syndrome test to get some cells from the fetus. But now you don't have to, thanks to this advance that Steve and a number of others have made. You can just take a blood test, and from there you can separate out what the mother's DNA is from what the baby's DNA is, and from that get a sense of, is the baby going to be healthy on a number of fronts. So it's really exciting work. That's of course only one of the things that Steve has done, and I'm sure we'll get into more detail on that and some of the challenges around that. Joe is also extremely talented and has focused his career on more in the area of infectious disease, right? So similar focus on genomics and a bunch of the areas where you've been very involved in building chips that have helped diagnose different infectious diseases, including SARS when that was first becoming a big and emerging threat. I guess this was more than a decade ago. But more recently, a lot of the work that you're doing is applying some of these techniques of kind of broad genomic sequencing, similar to the liquid biopsy stuff that we just talked about, to identifying infectious diseases in developing countries, both for public health and for medical research. And that goes to this ID-Seq project, which you've pioneered, but we're also working on as a collaboration with the Chan Zuckerberg Initiative engineers to bring that out. So I'm really excited to be here with both of you guys to go through some of the work, but also a lot of the challenges. So I'm curious though to start off with, maybe you could each just go into a little bit of detail about what you think are some of the most exciting developments that are going on today. It could be some of the stuff that we just touched on and how that could extend in the future, or it could be something completely different. So I don't know if you want to kick us off. Go
Sure. Well, just to pick up the cue from what you were saying, I think this field of liquid biopsies is poised to really emerge and transform healthcare in a way that creates health equity. Right now, if you're lucky enough to live near a major hospital with, high-end doctors, you get the benefit of that. If you're in a rural area, it's much harder to access that quality health care. And these liquid biopsies bring genomic technologies sort of to everyone, because blood can be drawn anywhere in the country and sent into a testing lab, and it helps everybody realize the benefit of this work. And as you mentioned, the sort of first and thus far most successful one has been around non-invasive prenatal testing, and that is now millions of women a year who are getting that test worldwide, and many thousands of lives saved if they're all avoiding amniocentesis.
Priscilla got that test, and that's how she got her test when she was pregnant.
Yeah. So I got interested in that area when I became a parent, and we were visiting the doctor, and the doctor says, "Do you want amnio? We recommend it." And we sort of sounded like a theoretical question. We have time to think about it. And my wife and I looked at each other and said, "Sounds like a good idea." Next thing you know, the guy was turning around with a huge needle and right in the belly. It was really terrifying. And there are negative health consequences for some people. So that's the first of what are, I think, going to be many tests. The next one I was involved in was for organ transplant recipients, heart and kidney and lung transplant. Is another way of replacing invasive biopsies for people who had those transplants and the doctors want to monitor the health. Infectious disease, I think, was something we both worked on, and that's clearly going places. And cancer is another one, which is probably a little earlier on, but in the next 5 years, I think you'll see these sorts of tests very widely used used in all sorts of aspects of cancer care.
So what's it going to take to get there on cancer? I know when you first started working on some of this, I mean, the hope was to do early stage cancer diagnostics, because of course cancer has the property that a lot of times it's not identified until it's really too late to do something about it. So if you can bring the diagnostic in and do it sooner, then you can usually handle it before it's going to be fatal or cause a lot of damage. But I'm curious, what are the gates or the challenges that make it so that this approach, which is already so accurate for detecting Down syndrome in babies or before they're born, what needs to happen on cancer?
Yeah, so I think you're right. And there's other ways in cancer treatment it can be used, but the most important would be early detection. And that's a tough one, and you sort of have to decide how good you want the test to be. And there's sort of challenging questions there. If you look at current early detection tests, like mammograms and PSA, their performance is really not that good. So it's not hard to beat them in performance, I think, for these liquid biopsies. But then the question is, to be a really good test, how the performance level goes up sort of another order of magnitude in order to reduce the number of false positives. The real question is you want to reduce the number of false positives so that people don't get a test, healthy people don't get a scare, basically. Yeah. And that's hard to get it to the level where, like less than half the test positives are false positives. That's difficult, and that's the challenge of the field, I think.
Yeah, so I mean, to kind of paraphrase this, and let me know if I'm getting this wrong. I mean, part of the issue on false positives is that someone once described this to me, that basically in our bodies there's always like a little bit of cancer growing, almost, that our body's naturally just going to beat back, right? Our immune system is going to beat back. But if you did a test that was perfectly sensitive and could identify any cancer cell or mutation anywhere, we'd all just get told that we had a lot of cancer all the time, yet most of it was not actually going to be an issue, and our body would have dealt with it. So you need to kind of get it at the stage where it's sufficiently problematic that we need some kind of external intervention, and not so early that we're just all getting scared about what's going on in our body that it'll naturally take care of. Is that kind of right, or do you think that's overstated?
That's the most interesting part of the false positive problem. There's also technical issues around false positives that have to be managed. But yeah, I mean, that's the deeper, I think, sort of biological or physiological aspect that the field is going to have to grapple with, that they haven't had to before because they haven't had measurement tools that sensitivity.
Yeah.
And we can see those are going to be coming, and it's going to be a lot of interesting frontier research to sort all that out.
Interesting. All right, so Joe, what do you see as most interesting on the horizon?
Yeah, well, riff on a little topics that Steve mentioned. Measurement tools are really important, and our ability to have accurate measurement tools changes what we can see and how we can see it. And I don't think anything has changed in the measurement tool area in biomedical science more than genomics in the last few decades. Specifically, our ability to sequence RNA and DNA. And while many people are familiar with sequencing DNA to find, inborn genetic mutations and things like that, the same concept of precision medicine can be extended to infectious disease, something I'm, very much passionate about, and cancer and other things as we discussed. And we can comment more on those afterwards. But in the area of infectious disease, in particular, it really begins to flip the paradigm when you use these new measurement tools. Instead of having the kind of the old model where you go to the doctor, you get a patient history, and the doctor sort of has to take that all into account and make some targeted guesses about what you might have if you've been exposed possibly to an infectious disease, and then send out for those assays kind of one at a time, hoping they hit the mark. Instead, genomics allows you to take a data-driven approach, an unbiased approach. That is, take the sample, look what's in it, and actually separate everything out that's from human from everything else, and ask the simple question of what isn't human, and get a completely unbiased view of what's in there. And that can really fundamentally end diagnostic odysseys that many people find themselves on, whether it be a rare infection or something that doctors just never considered. Mm-hmm. I can give you a small anecdote, for example.
Go for it.
You know, we had a guy come to a UCSF clinic. He was a construction worker. He had immigrated from Nicaragua some number of years ago, and he just had double vision and a really bad headache. And, you know, it's hard to work when you have double vision and so on. And they did a sort of a neurological exam, and sure enough, some of his cranial nerves were not acting appropriately. And, but that doesn't tell you what it is. It says there might be some kind of infection that's hurting his brain, giving him meningitis, infection of the covering of the brain, infecting some of those nerves. But based on his patient history, they said, well, maybe this is TB. You know, it could be Mycobacteria tuberculosis in the brain, put you on a large regimen of antibiotics and some steroids. And for a while, he did okay, got a little better. But then he got worse, and he got worse and worse. And he began to lose facial muscles, ringing in the ear, vomiting. He just declined precipitously. Repeat examinations of him and send out tests over and over again. Over the course of a whole year, failed to identify anything that was wrong with this guy. MRIs, imaging, dozens of PCR tests. And so ultimately, that activated a protocol we have that I had in my lab, which is basically we can accept patient samples that nobody can figure out, and then we can see if we can do a better job, and then return those results and confirm them with another assay. And so what we did is we actually took his cerebral spinal fluid, so basically the fluid that coats the brain and around the spinal cord, drew a little bit of that, and then sequenced the heck out of it. Basically, sequence all the RNA and DNA without regard to what's in there. Just do it all. And then let the computer sort it out. What is human? What isn't? Just separate it out. Find the needle in the haystack. Now, in this case, there was a lot of needles in the haystack. It wasn't really hard to figure out what this was wrong. Within about 20 minutes of getting the data, we knew exactly what this guy had. And it was sort of a good news, bad news situation for the guy. So at the expense of potentially grossing people out.
It's okay, go for it.
This guy had pork tapeworms in his brain.
Oof.
And that is actually a far more common problem worldwide than people realize. It's a global neglected disease. It's a disease called tinea, or neurocysticercosis. And you can get it by eating contaminated material that has the larva of the tapeworm in it. And it causes actually a great proportion, maybe a third of the world's epilepsy is caused due to this. And he had immigrated from Nicaragua, where pork tapeworm is endemic. But because he was seen here in San Francisco, he was out of context. No one actually thought that, oh, maybe this is pork tapeworm. Now, the good news is it's totally treatable. There's a drug, albendazole. He got on it right away. He's returned to work. He's leading a normal life. He's back to being himself. And so it's a story that's representative of a lot of stories that we have run in our lab, where you think you're looking for something, but it's something completely different. And instead of using intuition or being beholden to your own cognitive biases, you just let the data do the work. Let the computer figure it out. Because with this new measurement tool, we can really just scorch the earth and sequence everything.
Mm-hmm. Yeah, so I think there are a bunch of different interesting trends in there. I mean, one, or different points that you're making. One is, I think for a lot of diseases, we already have cures or ways to treat them, but a lot of the time the hard thing is just figuring out and doing the diagnostic, figuring out what the challenge, what the disease is. And then the vision that you've talked about a lot around hypothesis-free diagnostic, right? The idea that, today, if a patient goes to a doctor, the doctor tries to come up with a guess of what you have, and then they run specific tests to see if you actually do have what they think you have, and then figure out how to treat it. part of the goal of the work that you're doing is to make it so that you do a blood draw, you sequence everything that's in there, and then without having to come up with a hypothesis ahead of time, you can basically just have a computer spit out the results of here's what I found, here are the viruses, here's the eventually cancer types or different types of issues that are there. So that's a very promising vision for the future once we can work through a bunch of the issues in there. Now, I'd like to kind of transition to talking about how there are a bunch of broad trends across society that I think are having impacts not just on science, but a lot of different parts of society and policies and things like this, but they also impact science. So it's everything from advances in technology and computing to social issues like the erosion of a sense of truth and trust in experts. I mean, that's obviously something that hits science a lot, to even things like the trade war that's going on right now and the tension between our country here in the U.S. and China and others, and how that affects something like science, which is it's globally collaborative. So I'm curious to go through these, and if you have other things that you think are interesting global trends that we should cover as well. But I think that the impacts on science and how science can maybe contribute to making to addressing some of these problems may be somewhat counterintuitive to a lot of folks. So maybe let's start with what might be the simplest of it, is just the impact of technology and compute on scientific progress. There are a lot of people who argue that with more compute power we can do a lot more. There are also, I've seen arguments recently that some people think that the pace of scientific progress is slowing down. So I'm curious what you guys think about this. What's the broad trend over the last 20 years or so? What can we do now that's better than it used to be, and what's harder?
In the pace of scientific progress generally?
Yeah.
Well, that's a really tough question because different fields go at different rates, right? It's not like it's all moving in lockstep. 20th century was great for physics. 21st century is going to be great for biology. And even though physics has largely slowed down, there's areas of it that are very exciting, and areas that have been open problems for a long time. And a lot of excitement around the Gravitational Wave Observatory, for example. That's a bright spot in physics. But on the other hand, it's one where it's not that surprising. I think most physicists sort of expected UCM as a prediction from 100 years earlier.
I should say your background is actually as a physicist.
Correct.
Right? So
Correct.
You just transitioned into biology because you thought it was more interesting at some point.
I felt like the frontiers were expanding more rapidly.
Yeah.
And I feel good about that decision. That worked out for me. And within physics, there were probably areas that would have been smart to go into that had that same property, but not the whole field in general. And within narrowing it down to the last decade or so, in biology, as Joe was saying, genomics has been a transformative technology. And there's been 10 years of just absolutely revolutionizing the field of genetics. And it has moved an incredible distance thanks to genomic technologies. But those technologies are now going to be put into service to other areas of biology. Joe talked about infectious disease as one. Another example that we're also very interested in here at the Biohub is cell biology. We feel like measurement of phenotype is going to be transformed by RNA sequencing and other sorts of epigenetic analyses of cells. And we're at the beginning of that. And that's an area that's accelerating enormously.
Compute is really accelerating a whole array of different technologies. And without them, we couldn't do what we do. Most of the things I just described are made possible by advances in compute. And take an area that I'm not directly involved in, but I'm just watching next to it is just amazing to see, is cryo-electron microscopy. The advances in compute there let people understand the molecular structure of proteins and molecules at a pace orders of magnitude faster than in the last decade. And that's going to drive drug discovery, drug design, our understanding of underlying mechanisms of disease and everything. And that's fundamentally electronic, mechanical engineering advances, but really compute is at the heart of all of it.
Yeah. So I guess there are a couple of trends that you're talking about here. One is just the speed and price decrease in sequencing, right? So I guess the first DNA was sequenced. This was in the 2002.
The human genome.
It goes back to Sanger. First DNA sequence, first human genome.
Human genome,
2002.
First, okay. So 2002, human genome. Sorry, thank you for correcting me on that. And that was a. So that was.
That was $1 billion effort.
Yeah. it was only $1 billion. I thought it was
Three?
Yeah,
2 to
multi-billion-dollar
3.
effort, and took many years to complete.
It's order of magnitude estimate.
Yeah.
There you go.
Yeah, it's-
All right,
it's
so
sort of
but
a
now,
decade
so now we're
project.
here
Yeah.
though. It's on the order of less than 20 years later. And now sequencing a genome.
A couple $100.
Okay, yeah, and it's on its way down to tens of dollars, right? It's now at the point where you can do. I mean, that's the.
It's a million-fold decrease.
It's the fundamental, but that's the ingredient to do the liquid biopsy type work that we were talking about, or the ID-seq work that you were talking about. Is all that stuff starts with you take a sample of blood, you run the sequence, you can do it quickly. I mean, how long does it take now? It's hours, days.
These tests are turning around in a day or two.
Okay, so both it's getting faster and cheaper. And that will continue. But then you end up with a different bottleneck, which I guess is what you're saying, which is now, so you get the data coming out of this, and it's what? It's like gigabytes, right, for one sequence.
Yep.
So it's at the point where, I'm on the board of the Biohub, right, because Chan Zuckerberg Initiative is kind of the primary founder of it, although not the only founder. There are folks like Reid Hoffman who have also given millions of dollars to the effort. In our Biohub board meetings, one of the things that we talk about is the cost of the compute. And our AWS bill, for example, is like one of the specific.
You'll hear more about that at the next meeting, unfortunately.
Well, that's okay. We can. We call Jeff up and ask him about this. But it's interesting that the bottleneck for progress in medical research at this point, a lot of the cost in it is now on the compute and
Absolutely.
Data side, and not strictly on the wet labs or how long it takes to kind of turn around experiments, although that's obviously still going to be a big thing for a while as well. Yeah.
This is no more apparent than in the developing world or low-income resource settings, where actually the cost of the sequencing in the lab work has gotten to the point where you can do this almost anywhere in the world. It's gotten that cheap. However, the compute to be able to analyze that data is unfortunately not accessible to the vast majority of the people that do that. So it's very often the case, you'll go to one of these low-income resource settings, they'll have a sequencer, it's collecting dust. It's collecting dust because they can't compute. They can't actually do the compute side of it. And even if they could access the cloud, which many of them can, they can't afford that. And so, one of the primary initiatives that we've had here at the Biohub is to be able to address that bottleneck, to be able to overcome that compute barrier by providing really hardcore bioinformatic tools for these kinds of sequencing analysis at no cost, as well as training on how to use them.
Yeah, and that's why a lot of the approach at the Chan Zuckerberg Initiative has been around engineering, right? It's taking some of the lessons that I've learned from the experience in building Facebook and try to build a world-class engineering team that can help crank on some of these problems and make it efficient. But even then, we partner with folks like the Bill and Melinda Gates Foundation for your project on ID-seq that to do the public health part of this, right? Because it's expensive to do the compute and to get the equipment out and do all the pieces that you need to. What are the other trends, or what do you think are the things, so maybe on the negative side of this, what is slower today, or the biggest headwinds from either from technology or just facing science more broadly that weren't in place over the last 20 years?
Yeah, I think technology is largely an enabler of science. And that's been true not just for the past few decades, but going back 5 centuries essentially. Many stories about that. And the headwinds we're facing now are more societal. You touched on some of them in your comments. Issues of international collaboration are becoming very challenging now, and the trade war hasn't helped in that, and science has been a little bit swept up in that. And it's been, certainly I hear from my colleagues that they're frustrated with sort of publishing with authors internationally, having collaborations, especially in China, but not exclusively in China, and that's starting to put a chill on what has been a very powerful set of international relationships.
So maybe go into a little more details or specifics if you can, because I would bet that most people who are watching this are not familiar with how the trade war or a strained relationship with China would filter down into policies that make scientific research harder. So maybe just go into a bit more detail on how that works.
Sure. science is a global enterprise, and it transcends borders. We train people from many different countries in our labs. We visit labs in other countries as scientists. We publish papers together, and so it's sort of both the teaching and sharing of the knowledge we get with each other that advances the whole field. And now the trade war has sort of started to limit that in the sense that China has been a very bad actor industrially. I think no one is debating that the commercial terms which they've engaged with other countries, stealing technologies, inventions, things like that, have been really negative and not helpful. And the U.S. I think is justified in being concerned about that. But with science, at the end of the day, there are no trade secrets. We publish everything we do, we share it freely, and a large part of what we want to do is accelerate human knowledge. And so there's not as much to be afraid of there. And in fact, it slows down science when it becomes harder to talk and collaborate. And so simple things like you publish a paper. You sort of have an obligation to share your reagents with people. They write you and ask for them. I'd like this plasmid or whatever. And now some of the funding agencies in Washington are making that much more burdensome. Like you need to get their approval to send it out. There's places they don't want you to collaborate with. And so there's kind of new sets of regulations coming down at a very granular level that's kind of inhibiting people from full and open collaboration.
And so you mentioned some of the industrial issues in the U.S.-China relationship, but one of the concerns that I think has come up on the science side is there's a question around ethics and will advances that are being made be applied ethically and with the same standards in these different countries around the world. So, what's the kind of case on the other side, or I don't know if you just think that this is too far-fetched for why. For how you'd handle some of those issues, if not to try to put friction into the collaborations overall.
Yeah. So, that's a legitimate question to worry about because, ethical bodies are sort of done at each country specifically, and there's not a global scientific ethics thing, and so there's sort of different standards for sure. And I think the systems in place are pretty good. So if you're in a collaboration that involves human subjects or something like that, your university is going to look at what you're doing as part of this collaboration. So your part of it is going to be looked at with U.S. standards.
Yeah. So and what are you seeing as the implications of this on collaboration outside of China? So at the Chan Zuckerberg Initiative, we do a number of collaborations, I think, with folks across Europe. I don't know if we do much in China, but those seem to be going well, right? And those are kind of good partnerships. We value working with some of the top institutes in the world are in Europe. How is that going? Is that being impacted too from your perspective and what you see, or do you think that this is primarily a China thing?
It's hard for me to know totally. My sense is those are going to be impacted because the regulations that are coming are for all international collaborations, but most of the cases that are coming up are China-related specifically, and so there's obviously very complicated high-level politics going on around all that.
Yeah. All right, so maybe moving on from the topic of kind of trade and how that impacts China, science, to this question around just truth and trust in experts, right? Which, of course, we see affecting a lot of different parts of society. It's there's a big crisis and a lot of questions around journalism and high quality journalism. Obviously, Facebook and the work that I do most of my life is at the center of a lot of these questions around what is the role of social media in combating misinformation. But there's the version of this for science too, which it kind of plays on both how do we trust science and how do we in the work that we're doing build trust in science so that way people can have faith in the work that's being done. And I guess that there's this broader trend of people probably trusting experts a little bit less now than they would have 10 or 20 years ago in general. So I'm curious what you're seeing on this. What responsibility do you think scientists have or people who are leading scientific institutions like you are, or funders of science, which we are. What responsibility do we have, and how can we best kind of combat this trend, which I think is a really important and negative one?
Yeah, absolutely. You know, distrust in science is something that's been gnawing at me for some time. And it's obviously a very complicated issue. I think that there are many things that influence whether you trust something in science or not. One of those things is just being scientifically literate, being able to understand the information that you're given. And then fundamentally, do you have access to that information? I mean, I think it's pretty obvious that if you don't have the facts or have the information, you're not able to make sound judgment or objective decisions about that information itself. And so actually, just having the facts is kind of a big deal. And in science, frankly, I think we're headed toward a big reckoning here. Because where do you get your facts? If you have a family member that has cancer and you want to know more about that cancer or a clinical trial or how that drug performed, you want access not to what a panel on TV said about it. You might want to look up the actual facts and research the primary literature. And the fact of the matter is, today, is that much of our scientific record is held by for-profit publishing companies as their private property in perpetuity behind paywalls, even though your tax dollars paid for that science. And so what we're headed towards now is a reckoning with this issue, and that the trend towards publishing things open access, that is not behind a paywall, I think is really going to be critically important for the advancement of scientific literacy and building trust in science. And so this is a big deal. It's been the case for hundreds of years that these publishing companies, which served a much more legitimate purpose in the past when it was printing paper and distributing journals and things like that, is very different now in the electronic age. And it's hard to justify what they do and their profit margins in today's world.
Yeah.
So we need to change that.
Yeah, no, I mean, I think there are a lot of issues around this. And one of the projects at the Chan Zuckerberg Initiative that we've funded is Bioarchive, and the whole preprint movement to make it so that even, I mean, you're talking about one part of the issue, which is the closed nature of the publication. The other part, of course, is that it's slow, right? You go and you publish something, and then by the time that it gets reviewed and one of these companies gets around to publishing it, you might have burnt a year of other good scientists' time studying a similar thing when you already had the result to what they were studying. So the preprint not only makes it open, but makes it so that the turnaround time can be a lot faster, and iteration time matters a lot.
Absolutely.
But one of the ways that I've kind of thought about this issue in trust in science is they're almost, this may be oversimplified, but I think there are some people who say, okay, well, you should always follow what the current state of science is saying. And then there are a lot of people who say, hey, scientists get it wrong. And it seems to me like the reality is somewhere in the middle. The current state of science is our best understanding of the world, but a lot of it is likely going to be improved upon or proven to be not wholly right in the future, yet still your best bet when you're making medical decisions for your family or kind of decisions in any part of your life, it doesn't have to be medical research, is your best bet is to basically go with what the leading research has been at that time, even knowing that some of it will end up being proven false in the future, because other than that, you're just kind of going randomly. Yeah. So one of the things that I guess I worry about, and I'm curious if you share this, is I do think in those two sides of the debate, some folks are you should always follow and like science is accurate all the time versus, hey, I don't know if we should trust this. I do wonder if there's a responsibility to on the part of science to sometimes not to make sure that we don't overstate things, right? And I know this is something that you've talked about a bit in our conversations about how well I'd love to hear it in your words, but an issue that you've observed in the field over the last decade or so.
Yeah, there's a lot to unpack there. I mean, I worry that there's loss of trust in experts, when it comes to science. It's a loss of trust and objectivity, and in the process of science, and it's a different thing. So within science, you should always be skeptical. This is sort of fundamental tenet of science, to be skeptical. My mentor used to tell me, never trust anybody, especially not yourself. And there's a lot to that. You question, and this is how science advances, by questioning other people's results. You question your own results, and that's just an essential part of what the field is. And so it's not that you're saying trust experts, it's saying trust the process of science. And another way that's sort of frustrating right now that I think we could communicate better to the general public is around that. And Rob Phillips at Caltech has a very nice way of saying it. He says science is not a buffet. All right, you don't get to pick and choose what you believe. And there is truth. And if you want to have jet airplanes to get you around the world, and you want to have cell phones, and you want to have the internet, well, you've also got to accept vaccines and evolution and climate change. It's all the same intellectual edifice. And I think that's been lost right now. We failed to communicate that to the general public as scientists.
And what are some of the issues where you feel like a result gets overstated, or because I think part of what might hurt trust is that, right? I mean, there are, the advances that led to the internet or to jet engines or vaccines were obviously huge advances that when those things were figured out, it had a many-fold improvement over whatever the current state of the art is. Yet a lot of what I see on a day-to-day basis is, people publish results that might be a small % improvement over something with not a lot of, often it's very hard to reproduce, right? So it's hard to know if something was idiosyncratic to the data set that they used. And a lot of time it gets picked up and characterized and summarized, even if not by the scientists themselves, but by people covering it as if it's some kind of definitive proof of something, even if the effect size was small. Yeah. And I wonder how do we push back on that? Because it seems like you want to separate between the things that are truly transformative and major improvements and things that really might be marginal or might be nothing, and likely are overstated. And I think that's kind of, when people hear about this, if something gets overstated and then it ends up not working out, then that's how people lose trust.
Yeah.
We've got to do a better job on science communication. It's about science literacy and science communication. And the way that science is communicated to the public now is really important. My daughter reads something in the popular press. Hey, Daddy, they discovered something about this. And my first question is, did someone else reproduce it? Is there another lab that confirmed it?
Or where does it fit in the context of the 100 other papers on that topic? This is often where things get out of balance, right?
Yeah, and those are often not communicated in the style of the common media. And I think we could do a lot better on how we communicate science to the public in the nuance and in speaking to the truths about reproducibility and the fact that things have to be done over and over again.
Yeah. And I think there's a responsibility of the press as well, and not trying to sensationalize the latest paper that came out and overstating it and forgetting the context in which it sits of often a literature of many histories. You were mentioning vaccines, and that's one where these issues are coming up all the time right now, and all these elements are part of that story. So the whole vaccine autism sort of
debacle.
Misconception debacle. Yeah, this started from one paper published by Andrew Wakefield with a very small number of participants. It was a result that disagreed with hundreds of other papers, people who studied for decades the effects of these vaccines. And that one paper, the press jumped on, didn't put it in context with the rest, and then popular culture picked it up, and it created a situation where now lots of people aren't getting vaccines. It's really detrimental to society.
It speaks to this concept of sort of expert consensus, right? And it ignored the expert consensus. I think Lewandowski and others have written about this. But basically, if you're approaching a bridge and 97% of bridge engineers say, hey, the bridge is unsafe, should you drive across the bridge? Right? And if there's that 1%, that one paper says, well, maybe the bridge is okay. You're not taking, most rational people would probably take the consensus results. Say, maybe not today, I'll cross the bridge.
And there's no room for nuance in the discussion either, because as I think you were hinting at, not all vaccines are equally efficacious, right? And some work really, really well. Most of the ones we're supposed to get are really tremendous. I'm up to date on measles, tetanus, typhoid. In the last year, those are all ones I've had because they work really well.
And measles encephalitis can ruin your whole day.
Yeah, the disease, not the vaccine.
The disease, yeah.
The vaccine is terrific.
Yeah.
And with the uptick of people not getting vaccines and uptick of measles cases, everyone should be looking. I got measles as a child, and my doctor had my titer checked. I had the vaccine as a child. Doctor said we better check your titer. No sign left, so I had to go get a booster.
Interesting.
Got
my flu shot yesterday.
Yeah, well, that's one where
Shout out to everyone watching. Go get your vaccine.
Yeah, that's one where it performs less well, though. I think flu, in comparison to the whole rest of the battery, is significantly poorly performing, and it's not good if we don't acknowledge that as well and say that this is an area where we can do better, and we should be spending a lot of effort.
Performs less well, you mean the measles vaccine definitely prevents measles. The flu vaccine at the beginning of the season, the scientists and people in charge of managing infectious disease have to kind of make an educated guess at what strains are likely going to be big, and then they put it into the vaccine, and then you get vaccinated against those. So they might be wrong, but it's not going to harm you.
Generally not. That's right. Not harmful.
Yep, and may have some beneficial effect for some segment of the population. It's better than none. This is a really important point. And the important point is that these are the kinds of things that are a public health issue. And it's one of the areas that I really feel strongly about. In fact, that I think that we should recognize the fact that if you want public health policies to succeed, they basically have to be mandated. You cannot leave it to the individual to enforce those public health policies, or they will fail.
Interesting. All right, so I want to move on to another topic, off of the broader issues and maybe a little more futuristic. So let's talk about wearables and implantable technology. So this is something that I work on and I'm interested in on the Facebook side too. We've also had a bunch of conversations on the science research side. Facebook recently, we made this acquisition of this company, Control Labs, that basically is a wristband that can digitize signals that are coming down from your motor neurons. So the goal is to eventually make it so that you can think something and kind of control something in virtual or augmented reality with it. They actually have a dev kit of this working already today, so it's not like far off science fiction. But one of the big questions, and I mean, they have a great team of computational neuroscientists, and they really believe that the best approach to neural computing is wearable versus putting something inside you. Now, other people, I think that there's Neuralink as the company, for example, are experimenting with approaches that are implanting something in you, like literally drilling holes in your head, putting something in your brain, trying to pull signals that way. And of course, it's not just getting signals from the brain. I mean, there are things for managing a number of health conditions. And I'm curious, I think it would be useful or interesting to have to hear your thoughts on where are the boundaries between where something is better as a wearable versus implanting in you. What are kind of the challenges that need to be overcome with implantables, and kind of how do you think about that broadly?
Can we do it? All right.
You go first.
I'll go first.
I have my own thoughts on this, and they probably will differ from yours.
Okay. I mean, it's definitely a higher barrier to get to an implantable, I think. And, my personal...
I hope so.
Yeah, exactly. Because of the risk. There's a health risk involved in the procedure.
Yeah, of course.
And, I think those are probably most useful in cases where you've already got a medical condition, usually chronic conditions and things like that need to be monitored and managed in ways that you can't get the information any other way. If you could get it from a wearable, I think that'd be your first choice. But if you've got to measure pressure in your coronary system or something like that, your pulmonary system, sometimes you've got to be inside to do that. And there's devices that do that now, and they're going to probably be more broadly used over time. And you'll see, I think, their role in management by talking to external devices and things get a lot more sophisticated. But I think for the largest number of people, the wearables are going to have the most impact because it's just non-invasive and
so what are the problems though that you think you need to be inside the body to get?
Well, one of the obvious ones is getting direct access to neurons. And I think some of the most dramatic advances that we've seen over the last year in this area are, for example, Eddie Chang's work at UCSF, where, again, you have to take the skull off, but an implantable sensor array can actually decode in real time inner speech. So think about aphasic people, people who can't talk because they've had a stroke. This sensor array can literally decode inner speech. So you think a sentence, and with very high accuracy in real time, it can read it out. And those kinds of accuracies and that kind of detailed real-time information has never been possible from surface readings. You actually have to get under the skull and touch neurons. And I would say that the same is going to be true for certain kinds of neural prosthetics, for very complicated motions. Playing the piano, for example, is going to require direct interaction with neurons.
These are people who are very sick, though, who are paraplegic,
like I said,
paralyzed in some way,
aphasic,
right?
not able to talk.
So,
I think the worst one that I've ever heard of is called locked-in syndrome, where you're completely paralyzed, but you're cognitively active. So imagine those people if you could provide access to the outside world through a neural link.
Yeah, well, especially if your brain is not able to send out motor neuron signals. I mean, part of the theory that the Control Labs team has is that it's pretty much all animals have motor neurons, right? And it's humans are somewhat unique in having the neocortex and the thinking part, the reasoning, but every animal moves, and because of that, it's actually one of the areas of our biology that has the most redundancy, right? If like a neuron gets damaged, there's plasticity, and your body can remap it to something else, which means that your body also has excess capacity to be able to, just like I can move my hands around. I have enough kind of neural capacity and my motor neurons to probably control another extra hand, and it's just a matter of training that, and then they can pick up those signals off of the wrist.
Yeah.
But obviously, if your ability to translate things that are going on in your brain into motor activity is limited, then you need something implanted. But
no, I think you're right. The peripheral nervous system is going to be really useful for wearables. Scott Delp at Stanford has been developing wearables to control tremor diseases and things like that, where your hand shakes, and using feedback based on measurements of a wearable on the peripheral nerve. And that all looks very promising.
In fact, one of our Biohub investigators, Ricky Muller, is doing implantable closed-loop deep brain stimulation. In fact, deep brain stimulation is one of the areas where people are walking around today with implantables in their brain, mostly for motion disorders, but also now for depression and many other things. And actually having a closed-loop system, like Ricky works on, that can actually monitor what's going on in the brain and then modulate that activity in real time, I think is very powerful, and it makes a strong case for an implantable that's below the skull. And depression is not exactly, infrequent either.
Yeah. So what about outside of the brain? So you mentioned the heart, but I mean, what are some of these things? Well, I'm curious if you have examples in mind that you think would be interesting, but I'm also curious to go through some of the challenges of this. I mean, it's our body basically treats anything that's foreign as something that needs to be quarantined and kind of boxed off, right? So, what are some of the? So, where do you think this would be useful, and what are some of the challenges that need to be overcome to make this something that can actually happen over time and have a lifespan that's beyond, a year?
Well, some of the best examples are stents and pacemakers, right? Stents will go in for 20 years or more, and they're passive devices, so don't need power or anything like that, but they're able to be there in the body for very long periods of time and not be completely rejected. Pacemakers similarly have fairly long implantation times, and so those are examples of what you can hope to aim for with more complex devices. And I think you'll see them in areas like pulmonary and cardiovascular disease for sure. That's where there's been the most history, most medical need, and where there's a very bright future.
And how do we deal there with the problem of the immune system attacking foreign objects in the body? Why do those last for 20 years, but other things that might be implanted have significant, bigger challenges?
A lot of it is the material science of the devices and what you can do around that to control. And if you want the device to be sampling from the body, then you have interfaces that are harder to control. And so a lot of it is design specific, I think. Other parts of it, I think, are lifetime related with batteries and
I see. So your point is, if you want to have something in your blood, right? So take, for example, like the liquid biopsy thing that we talked about before, but some version of this like 30 years from now, that's not just a one-time test, but like a permanent thing in your body. That, I mean, I don't even think that there's any roadmap to be able to get to this in 30 years. But in theory, you would want something that could on an ongoing basis monitor what's going on in your body and alert you if there's something that you need to go deal with. But in order to do that, in addition to like many other problems that you would need to deal with on the path to that, it would have to have an open interface to the blood. And when something has an open interface like that, it's just more when the immune system tries to box it off, which I'm sure there's a more technical term for than box it off.
Product growth, yeah.
It's tough to keep those interfaces open. All right, so
biocompatible material science is where it's at, and being able to have these electrodes or interfaces stay fruitful for a long time is really a huge challenge. The arrays and sensors that we have today have a very short half-life. They get blocked off, as you say, they lose functionality, and until that is solved, and it's really a biocompatible material science problem. And I would also say that you're going to want to have these things passively powered. You can't have batteries in there. That's sort of unrealistic. And so how do we get passive power transmission?
Well, Ada Poon, one of our investigators, has been
I was just about to mention her.
Yes. Oh, there you go. Sorry, you're setting it up.
You jumped the gun. So Ada Poon, one of our investigators, is developing new ways to harness ambient Wi-Fi and other power transmission modalities to power nano devices, in which case you don't really need long-lived batteries underneath the skin. And that's going to be really critical.
Yeah, that's really interesting. All right, so maybe one more topic before we wrap. So the Chan Zuckerberg Initiative for Science, we kind of have this very long-term goal, which it's going to take a very long time to get to, but the hope is to help the field of science to cure, prevent, or be able to manage every disease, hopefully within our children's lifetime, or by the maybe by the end of this century. And I mean, I think there's a lot of debate about whether that's possible to get to. There are kind of there's a lot of different diseases, but there aren't that many different categories of diseases, right? So we've talked about infectious diseases, cancers, people die from accidents. There's obviously the neurological and neurodegenerative diseases. I'm curious from each of your perspective, what do you think needs to happen over the next, 20 or 30 years to get us on the path to being able to achieve that goal?
Okay. So when you look at the global burden of disease around the world right now, sort of by whatever statistical metric you care about, they're sort of dominated by two broad categories. One is infectious disease. The other are diseases that relate to disorders of the cell. And there's a lot of what you just mentioned fall into that. And so if you're thinking on a 100-year time scale, to reach that second category, what you should be investing in now, and what we decided to do with the Biohub, was make a very strong investment in understanding cell biology. You understand the basic biology of cells, you'll be able to then use that to understand and hopefully correct and cure these diseases. And that gets a big piece of the puzzle right there.
Absolutely, and investment in tool building. Like having tools that let you do that next thing at a accuracy or proficiency logs better than you can do now is critical. So how do we make vaccines? How do we design vaccines? In the past, it was sort of hit or miss. Get the bug, inactivate it, make the immune respond to it. And that works for some things, and for polio and measles and many other things, it's been a huge success. For other things like malaria, it's been a lot tougher. And we need to be smarter about how we do that. It's going to be limited by our ability to see the molecules. It's going to be limited by compute. But if we can design immunogens, the thing that elicits the immune system, to create antibodies that we already predetermined, broadly neutralizing antibodies, for example, antibodies in your immune system that can actually prevent HIV or prevent forms of dengue virus or whatever infectious disease you care about. That would create a whole new area of vaccinology and immunotherapeutics that we can't even imagine right now today. But we know that the power is there to do it. Human beings naturally generate these antibodies. If we can understand the fundamental rules about how they do that, when they make a good antibody from a bad antibody, we can play the same game.
It'd be a game changer.
Total game changer.
Totally transformative.
So how do we get there?
So one is to understand how when a rare individual does make that 1 in a million antibody that tends to be like really good and neutralize all the forms of dengue virus, or HIV. HIV has been one of the toughest ones to do, or malaria, a parasitic disease. We have to understand what were the rules by which that immune system evolved to that point. How did it get there? And if we can create a molecule that can walk the immune system down that same path to end at the same antibody, then we can help everybody's immune system do the job itself, rather than giving people a medicine or small molecule, which are also very important, don't get me wrong.
And Peter Kim, who's been our lead advisor on the Infectious Disease Project, has really fantastic ideas there and is taking the steps down that path.
Absolutely.
Right?
He calls it immune focusing.
Yeah. So you mentioned the strategy of building tools, right? So if the goal over a 80 or 100-year period is to dramatically accelerate the rate of progress, and part of how you do that is by giving scientists better tools that they can inspect things in more detail, can do the computation that they need to faster, et cetera. I mean, obviously, at the Chan Zuckerberg Initiative, we're not actually doing the science directly. Our whole mission is around empowering scientists to make these to make this progress. I'm curious, what are the things that you think need to happen to accelerate scientific progress the most? Whether it's like specific tool development, things that you'd like to see in the field, or just overall in order to kind of get closer to this mission.
Well, you touched on it earlier, I think. One of the ways that we spent a lot of time thinking about how to accelerate science as we were all planning the Biohub together, and accelerating communication through preprints. I mean, that's a big experiment we're doing, and all the research we do and all the research we fund, people have committed to accelerating the sharing of their results through preprints, which, if you do the back of the envelope calculations, could be even a factor of 5 increase in the speed of discovery over a decade or two. So that, we think, we're really interested in seeing how that works. But also, I think, just really recognizing that scientific discovery is often driven by the development and application of new technologies. And sometimes in the narrative, that gets a little bit swept under the carpet. But I think bringing that out and recognizing it and saying we're going to explicitly invest in that and try to develop the next generation of tools, whether it's compute-based or novel forms of microscopy or the next generation of genomic tools, and helping people use them in their research.
I'd make a pitch for fundamental discovery, basic science, and curiosity too. That sometimes you're studying something, or you have a scientist is studying that's very basic. It's not obvious to see how it would ever be applied in the real world. But sometimes that fundamental investigation, that discovery, or that dissecting of really basic mechanisms can lead to quantum jumps that no one ever expected. I mean, just in the last decade, Jennifer Doudna and others have, studying phage, viruses that infect bacteria, no real obvious play on how that would affect human health or disease in any real way, unleashed the revolution of CRISPR and gene editing. And that came from basic science without an obvious applied goal. And so there's a role for fundamental curiosity-based investigation in everything we do.
All right. Well, I think this has been great. I think we hit a lot of topics. I'm really excited about the work that you guys are doing. Thanks for joining me today.
Thanks for having us, Mark.
It's been very fun.